When most people imagine Texas energy, they picture the open deserts of the Permian Basin. But hundreds of miles away, beneath the forests of East Texas, drillers have reached a very different kind of gas field. It is deeper, hotter, and under so much pressure that a successful well may release far more gas than the formation surrounding it. Some targets lie nearly 3.5 miles underground. Almost all the potentially productive territory remains untested. And unlike many remote gas discoveries, this one sits close to the pipelines, industries, and export terminals, capable of giving it global importance. Recent drilling results have now forced scientists to reconsider an enormous petroleum system extending beneath the Gulf Coast. But the same pressure that makes this resource so promising may also be the reason much of it is never developed. Because this is not simply another Texas gas field. It may be the newly recognized edge of something far larger. West Texas dominates America's oil story. East Texas, however, belongs to natural gas. Near the Louisiana border lies the Haynesville-Bossier region, where horizontal wells reach organic-rich rock more than 10,000 feet beneath the surface. Even the names can become confusing. The interval called the Haynesville in Louisiana often correlates with rock called the Lower Bossier in Texas. Other Bossier layers sit above it or extend farther west, creating a stack of related gas-bearing formations rather than one clean underground boundary. But the complicated terminology hides a simple reality. Deep beneath East Texas, gas exists throughout an enormous volume of shale. It is not stored inside one giant cavern. It occupies microscopic pores and fractures spread through the rock itself. For years, companies concentrated on the best understood parts of the system near the Texas-Louisiana border. Then, drillers began moving west, and the farther they moved, the more unusual the formation became. More than 140 million years ago, the modern Gulf Coast looked completely different. Warm seas covered the region. Organic material from microscopic marine life sank through the water and mixed with mud on the seafloor. In areas with limited oxygen, much of that material escaped complete decay. It was buried beneath additional sediment as the Gulf Coast basin accumulated layer after layer of rock. With greater depth came greater heat and pressure. Over millions of years, the organic material gradually transformed into hydrocarbons, primarily natural gas in the deepest and hottest sections. Some of that gas migrated into porous reservoirs, but much of it remained locked inside the dense shale that helped generate it. And in one part of East Texas, the gas remained trapped so effectively that pressure continued building long after the rock formed. The result was a formation that contained not only large quantities of gas, but enough underground pressure to change how that gas might eventually flow. For most of drilling history, however, knowing the gas existed did not mean anyone could produce it economically. Shale contains gas, but it does not release that gas easily. Its pores are extremely small, and the rock has very little natural permeability. A traditional vertical well may contact only a narrow section of the formation. Horizontal drilling changes that geometry. After descending for miles, the well turns sideways and continues through the gas-bearing layer. Hydraulic fracturing then creates pathways connecting the well with a much larger volume of rock. This combination transformed the established Haynesville into one of America's major gas-producing regions. But shale is never perfectly uniform. Thickness changes, organic content changes, natural fractures become more or less common, and the temperature history determines whether a section contains oil, wet gas, or almost entirely dry natural gas. The western edge of the East Texas Basin contained one difference more important than all the others. The gas was trapped under extraordinary pressure, and pressure can turn an overlooked rock layer into an entirely new drilling frontier. All underground reservoirs are pressurized, but in this western area, the pressure is far above what would normally be expected from depth alone. Scientists identified a zone of highly overpressured, fractured, high temperature, and organic-rich Bossier shale along faults marking the western side of the East Texas Basin. Industry often calls this area the Western Haynesville. But after examining well logs, seismic data, and the precise depths at which horizontal wells entered the rock, scientists concluded that much of the gas was actually being produced from the Bossier Formation. That may sound like a technical naming dispute. It is not. Correctly identifying the rock changes how geologists map the resource and how much potentially productive territory may surround the existing wells. And the small number of wells already drilled there produced another clue. Their estimated lifetime gas recovery appeared significantly higher than that of typical Bossier wells. The pressure was helping force more gas toward the well, but pressure works in both directions. It can improve production. It can also make every mistake underground far more expensive. Some western Bossier targets approach 18,000 feet beneath the surface. Reaching them requires more drilling time, stronger casing, and equipment capable of surviving extreme underground heat and pressure. But difficulty alone does not explain why the formation remained overlooked. East Texas already contained more familiar opportunities. Companies could drill established Haynesville and Bossier areas, where years of production had created much better information about costs, decline rates, and expected well performance. The western target, therefore, did not merely need to contain gas. It needed to produce enough gas to justify ignoring safer and better understood formations nearby. A formation does not need to be empty to be overlooked. It only needs to be more difficult than the formation next to it. But if the early western wells could be repeated across a larger area, the result would not simply be another Texas gas field. It could create a new supply corridor toward the Gulf Coast. And once scientists examined how much untested territory surrounded those wells, the previous understanding of the Bossier no longer made sense. Scientists did not treat the Bossier as one uniform field. They divided it into 3 continuous shale gas areas and 1 conventional oil and gas area. The established producing region around the Sabine Uplift became 1 unit. The enormous, lightly explored territory surrounding it became another, and the deep, overpressured zone on the western side of the East Texas Basin became a separate assessment area. That western area was especially uncertain. Only a small number of wells had directly tested it. In the scientific model, approximately 99.7% of its potential production area remained untested. That does not mean 99.7% will eventually produce gas. It means scientists had very little direct drilling evidence across nearly the entire area. They had to combine geology, early well performance, expected well spacing, possible success rates, and estimated lifetime production. The result was not one guaranteed quantity, it was a probability range. But the size of that resource would only matter because of what was already being built above it. Natural gas only has value when it can reach a buyer, and East Texas sits unusually close to one of the fastest growing gas markets in the world. The Gulf Coast contains power stations, petrochemical plants, and liquefied natural gas terminals capable of cooling American gas into a liquid and shipping it overseas. The wider Haynesville region already benefits from its proximity to these facilities. In 2025, 2 completed pipeline projects added a combined 3.5 billion cubic feet per day of capacity, connecting Haynesville production towards southeastern Louisiana. Additional LNG export projects are also increasing the amount of gas the Gulf Coast can send into global markets. That means the underground discovery and the surface infrastructure are developing at the same time. The pipelines are expanding, the export terminals are expanding, and beneath East Texas, scientists had just calculated how much undiscovered gas might be positioned to supply them. The first number applied specifically to the deep western frontier, and on its own, it was already enormous. For the deep western Bossier area, the formation industry often calls the western Haynesville, scientists calculated a mean of 203.2 trillion cubic feet of undiscovered, technically recoverable natural gas. That is the estimate most directly connected with the high-pressure Texas frontier. It does not represent gas contained inside one proven reservoir. It represents what scientists estimate may exist across the entire western assessment area. To put the scale into perspective, the Bossier Formation had already produced gas for years, but the amount historically extracted was only a small fraction of what scientists now believed could remain in this western area alone. And then, they widened the map. When scientists combined the western Bossier with the established producing area, the much larger peripheral shale, and smaller conventional reservoirs, the mean estimate reached 343.5 trillion cubic feet of natural gas. The wider probability range extended from approximately 103.9 trillion cubic feet at the conservative end to more than 601 trillion at the upper end. The central estimate is equivalent to more than a decade of total American natural gas consumption at recent rates, but the full 343.5 trillion cubic feet does not sit beneath Texas alone. The Bossier Formation extends through a much larger section of the Gulf Coast. What happened in Texas was more important than one state-level number. A small collection of deep, high-pressure wells revealed evidence that forced scientists to reconsider the scale of the entire formation. But even 343.5 trillion cubic feet means very little unless companies can produce it profitably. The most important words in the assessment are not the number. They are undiscovered and technically recoverable. Undiscovered means the gas has not yet been confirmed by enough drilling. Technically recoverable means existing technology could potentially produce it. It does not mean production would be profitable, and it does not make the resource a proven reserve. Before that can happen, companies must drill more wells, identify which parts of the formation perform consistently, and determine whether the gas can cover the enormous cost of reaching it. The Western Bossier combines unusually promising wells with unusually difficult operating conditions. High pressure may increase the amount of gas recovered, but it also requires more expensive well designs. Greater depth may place the rock inside ideal gas-generating conditions, but it increases drilling time and exposes equipment to extreme temperatures. The geology improves the reward and the risk simultaneously. No scientific assessment can determine which one will ultimately win. Texas does not need this formation to prove that it is rich in natural gas. The state already produces enormous quantities from multiple basins. What could change is the future geography of that production. The Western Bossier may provide companies with a new deep target near an existing network of roads, drilling services, processing plants, and pipelines. It could supply Gulf Coast industries. It could support expanding LNG exports, and it could extend the productive life of the wider Haynesville region as its most established drilling locations become increasingly developed. But none of that happens simply because scientists published a large estimate. Approximately 2,000 wells had targeted the wider Bossier across the onshore Gulf Coast when the assessment was completed. The formation had already produced around 3.8 trillion cubic feet of gas. The new estimate is vastly larger than that historic production. Yet the size of that difference reveals how much of the story still depends on future drilling. A resource estimate creates an exploration opportunity. Only production creates a gas boom. The gas field beneath Texas could change everything, not because drillers suddenly discovered one enormous underground cavern, but because a handful of wells revealed that a known formation may extend into a deeper, more pressurized, and potentially more productive frontier than earlier drilling had shown. It lies close to the pipelines, industries, and export terminals capable of giving that gas value, but it also lies inside rock, difficult enough to make every new well an expensive experiment. Scientists have now estimated what may be there.